All right. Let's get back to where I was. And here we go. So everyone can see the slide now?
Yes, sir.
Yes. Okay. So first I want to thank you for your interest. This is my first lecture to my colleagues in India. So I'm very excited about that. I have a number of mathematician friends who are of Indian origin. Manoj Chari, who works for SAS, and Radhika Kulkarni is a good friend. She is currently the president of Informs. I'll talk about Informs a little bit later. So today, the plan is I'm going to talk about careers in industry, and the normal term, and in fact I use this in the description, is to talk about non-academic careers. But recently I've decided that that's not a good term because non-academic has a negative connotation. So instead, we're going to talk about big careers, where big is an acronym for business, industry, and government. And that covers the vast majority of jobs and so forth outside the realm of academia. So let me first give you a little background about myself. So here I am telling you about how to prepare for working in industry, but the fact is my own path was not very well laid out, and I was not totally prepared. What happened in my case was that my father was a university professor, and so my plan was also to be a university professor. So when I went to graduate school to get my PhD, I took courses that were all about pure mathematics, so Banach space theory and esoteric subjects like that. But then my thesis advisor moved from the University of Illinois to Georgia Tech. And when I got down there, I was still working on my thesis, but in order to receive funding, I had to be enrolled in classes there. So I ended up, and I'd taken all of the math classes I needed to take. So I ended up taking an interesting assortment of classes in things like operations research and system engineering and different computer science classes and so forth, until I could finish completing writing my dissertation to get my PhD. And it turned out that was, although I didn't do it to prepare myself for industry, that was very useful as it turned out. And then, of course, keep in mind, my goal is still to be a university professor. So off I go to the joint mathematics meetings, which is where PhDs tend to go to find academic employment. And you sign up for interviews with the different universities, which I did. And I ran into an old professor friend of mine, and he was talking to this taller gentleman. And I said, "Bob, good to see you." And he says, "Well, what are you doing here, Alan?" And I said, "Well, actually, I just got my PhD and I'm looking for a job." And he says, "Oh, well, you should talk to Dan Wagner. He has a company of mathematicians, and they're here interviewing." So I talked to this gentleman, Dan Wagner, and eventually that led to being hired by the company, Wagner Associates. And, you know, my reason for choosing that path rather than the academic career was salary for one. It paid considerably better, I think roughly twice what I was going to make as a university professor. And I had a lot of student debts. I was actually married with 3 children at this point. And I said to myself, well, I can work at this company for a while, some real world experience, and that might help me to, when I go back to academia, help make me a little bit unique and so forth. And as it turned out, I enjoyed working for Wagner Associates so much, and I was able to indulge my desires to teach by teaching as an adjunct faculty at a local university in the evenings. And this eventually led to my becoming president and CEO of the company. So we'll talk a little bit more about that going forward. My intention is to speak for 30 minutes, somewhere around that. Could be a little less, could be a little bit more, and then take questions. So I'd like to spend the latter half of this meeting answering your questions. So please be thinking as we go along about questions you have and submit them through the chat. So brief background on my company, Daniel H. Wagner Associates. We provide consulting services in operations research, mathematics, and software development, and have been doing this since 1963. So the company is 60 years old, which is unusual for a small business. Not uncommon for large businesses, obviously, but businesses typically tend to grow and become a large business or go out of business over time. And ours has been successful in maintaining a reasonable size and yet being very well known within different communities, including the U.S. Department of Defense. There are 3 offices, one in Exton, Pennsylvania, which is the headquarters, Hampton, Virginia, and Vienna, Virginia. Hampton, Virginia is the largest office, and that's where I served most of my career. We work on large variety of problems. The majority are in the area of Department of Defense, and most of those are for the Navy. But we also do work in the area of mathematical finance. We actually have a couple of products, including a retirement spending planner and a mean variance optimization library. We do portfolio optimization. We do work for banks on loan valuation, so forth and so on. Within the area of Department of Defense, even across the different agencies, our primary focus is mission planning type projects and tracking and data fusion, multi-sensor data fusion in particular. So you have multiple types of sensors, radar, sonar, video sensors, sensors that detect electronic emissions, all that sort of thing. And in the past, each system operated independently, and the operator had to mentally try and put things together to figure out what the world state was. These days, we have systems that can take that information and fuse it together to build a world picture that then enables us to do a better job in our mission planning, defenses, and so forth. So the outline for the talk today is I'm going to talk a little bit about the difference between going into business, industry, and government and staying in academia. Now, I don't know exactly where you are in your academic life at this point. This part of the talk is really more focused on graduate student level, because if you are going on to get a PhD, you will primarily be encouraged to pursue an academic career. So the PhD level affords you the ability to teach at a university and do research in upper level mathematics. And it's quite common for new PhDs to pretty much only apply at universities, which of course was the path I described for myself originally. So in this part of the talk, I'll try and compare and contrast the differences between staying in academia and going into business and industry. Then I'll talk a little bit about, what it's like to be an industrial mathematician as opposed to academia. You have lots of experience of what it's like to be a student, and by observing your instructors, you have knowledge of what it's like to be an academic. But most of you probably don't have a lot of insight into what the life of a mathematician might be. Then I'll talk a little bit about preparing for a big career. What things can you do to improve the chances of being successful? And finally, I'll wrap up with a little bit of discussion on interviewing and interviewing process and so forth. In other words, great, you want to be an industrial mathematician. How can you be successful in finding the job that you want? So, what's the difference between working in academia and working in industry? Well, in academia, you can typically, you work alone, right? Other than your teaching, you go into your office and you work on some research problem, and you may have some colleagues that you sometimes consult with, but mostly you're trying to solve these problems on your own. In industry, it's just the opposite. You tend to work in groups, can be small groups, and occasionally you do work alone on a very small project. But more commonly, there's a group of people working on a given project. In academia, academic environment, teaching, research, and so forth. In industry, business environment, quite different. You are either a subset of a group that focuses on problems that are handed to you from upper management, or you may be in a small company such as my own, you would be involved in finding interesting problems to work on and being successful in convincing the client to pay you to work on those problems. Academia is all about proofs. Industry is more about solutions. In academia, you have complete generality and you get to select the problem. So you have an area of expertise and you tend to work in that area, but within that area, you can choose to work on any particular problem you want. Nobody's saying, oh, you have to solve this problem. And it's just the opposite in industry. You're often handed a problem, you're assigned a problem, and it's usually a very focused, specific problem. In academia, you're primarily interacting with other mathematicians. In industry, yes, you'll interact with your colleagues, many of whom will be mathematicians, but there'll be other colleagues who are computer scientists, engineers, other areas. And then, of course, you also have to deal with the clients, which can be upper level management, executives, could also be engineers and so forth, working for the organization that you're trying to help. So you have to interact on a much more broad basis. In academia, the most important thing is to be smart. You're really smart. You can go off on your own and work on these problems and solve some and write up the proofs and publish papers and so forth. In industry, it's much more important to be useful. You can be smart, but if you don't produce things that are helping your company, then that's not nearly as good. Again, pure research versus applications. In academia, the product that you produce is a paper or an article. And in industry, what you produce are algorithms and software that solves a certain problem. In academia, you tend to be a specialist. In industry, it's more important to be a generalist. You have to have a broad base in order to work on lots of different problems because you don't know what's going to come up next. And a big difference is in academia, your research is self-paced. You get to decide, how much you're going to work on something. Maybe you get stuck and you decide to put it aside for a while and so forth. In industry, you have deadlines. Okay, we have 1 year and 6 months to work on this project, and whatever we come up with by the end of that time, that's it. So there is a huge difference between working in academia and working in industry. All right, so what is it like working in industry? You're going to be working on projects, and the basic project steps always are define the requirements. What is the problem? What are the constraints? What are my goals? And once you have that, then you develop a mathematical problem formulation. So this is the math modeling step. How can I put this real world problem into a framework that's amenable to solution by mathematical techniques? And once you have the problem formulated, then you start looking for what kind of techniques can you apply, and you develop an algorithm. At this point in the process, the algorithm, is typically written on paper. And when I say written on paper, obviously you can write it on the computer. But you start with, here's the steps involved in solving this problem. And then the next step is to implement that algorithm. Typically, you start by building a prototype, because you don't know for sure whether the algorithm is correct, whether it's going to produce the kind of results that you want. So you build a prototype. The prototype typically uses a language or software that is not production level. Quite commonly, you'll implement the algorithm in an Excel spreadsheet, for example. Or you may use something like MATLAB, which is a simple computer language. And then you try running the algorithm, you see what it produces, and you analyze the results. So it may be that the algorithm you designed crashes and it's not working at all. So you have to go back and figure out what's causing that. And maybe it's giving results, but it's not the results you expected. The range of solutions is too broad. When you, for example, you might apply your prototype to a simple example where you know what the optimal solution is. And when you run the algorithm, it's producing something that's not anywhere near prototype. Not anywhere near the optimal solution. So you go back into the prototype and start refining the algorithm. Oh, okay, I see what I did here. I didn't take into account this case, and so forth and so on. And then when you believe that the algorithm is working as designed and it should be able to solve the problem, then you create a production solution. So you take that prototype and now you start coding it up in C++ or Java or whatever the appropriate language is for this particular application. And once again, that process involves a lot of testing. There's a whole suite of steps involved in classic software development, testing and refinement and iteration and so forth and so on. So you could be working on any given day at any level of these basic steps. So a typical day depends on where you are in your career as well. You might be doing some research, some writing, some sharing, teamwork, some coding. Maybe you're spending all day doing coding this particular day, or maybe you have a meeting in the morning that's talking about working on the solution to a particular project, or a meeting that's looking at the risks involved with a given project, so forth and so on. And you might spend an hour or two on that, and then go back to working on the coding or research or whatever. So you kind of, just as in the academic life, you spend part of your time in class and then part of your time working on homework and so forth. When you start out early in your career, you tend to work on a single project with lots of direction. So for example, if you came to work for my company, you would be assigned a project. You would meet with the leader of that project. They would say, okay, I want you to review the proposal that we wrote, so you see what the background is and what the problem we're trying to solve. And then I'm going to have you work with so-and-so on this project. They will mentor you and help you to contribute in a successful way. Then as you gain more experience, you might be working on multiple projects, and you might be doing so independently, less direction, certainly. So, that first project that you worked on, you developed a little bit of expertise in a certain area, and it turns out there are a couple of follow-up projects or related projects, and so the leaders of those projects saw what a great job you did contributing originally, so they want you to work on their project. So now you're working on a couple of different ones. And then eventually you you develop your own area of expertise, and you start leading projects yourself and directing others. So that's quite different from when you first started. So how do you prepare for a career in business, industry, and government? Well, you're doing some preparation already just by the coursework that you're taking and the technical skills you're developing in those areas. Your traditional math classes, such as calculus and linear algebra, maybe numerical analysis, things like that. For a career in business, industry, government, it's probably important that you take some probability in statistics, because the fact is that in the real world, problems are not cut and dried. They almost always tend to have a stochastic element to them. So there's some uncertainty involved, and being able to quantify that uncertainty and characterize it in a mathematically accurate probabilistic or statistical formulation can be important. So the better your gut feel for probability and statistics, the more successful you'll be. And that's pretty much across the board. I mean, it may be that in certain engineering disciplines, if you're working for an engineering company, the problems don't involve a lot of probability. But most of the time in the real world, there's enough uncertainty that even if you develop a a deterministic solution, the next step is going to be the client's like, well, you know, we don't really know about this part. It's kind of uncertain. Could you develop a solution that takes that uncertainty into account? And now you're dealing with probability and statistics. Again, a traditional math degree does not necessarily require you to take computer science and software, although that's changing at different universities. But having that background is going to help you when you're trying to apply your skills in the real world. So if you're thinking of going into industry, then having some background in computer science and software development is useful. You can always learn more once you are hired, but that's going to help to get your foot in the door, so to speak. And of course, these days, another area of applied mathematics that is booming, and lots of jobs in this area, is the area of data science. And I say that in a broad sense, so I mean analytics, business analytics, other types of analytics, data analysis, advanced data science subjects such as things like artificial intelligence, deep neural networks, machine learning, and so forth. And then something else I would encourage, and we'll see this when I talk about interviewing skills, is if you have an interest in going into different fields in industry, it helps to take a course or two outside of your major or your minor even. So taking a course in economics or physics or chemistry or anything like that helps you to see the application of mathematics in a different field. And that's going to prepare you for a career in business, industry, and government. So in addition to your coursework and technical skills, there are soft skills. So being able to communicate well in a written environment comes up a lot because you're going to be required to document your work often, write up the things that you're doing, and so forth. You may have to write up reports to clients. Here's what we did this month in this area, or here's what we did since the last time we gave you a technical briefing, so forth and so on. And then again, later in your career, you'll be writing a proposal to a client saying, if you give us this much money, here's the work we can do for you. So being able to write well is going to make you more successful in your career, both at the beginning and in the latter part of your career. The same thing is true with oral communication. You'll be giving presentation to clients. You'll be giving presentations to your colleagues. So, for example, as a mathematician in my company, we have mathematicians and computer scientists or software developers. And the mathematician will come up with an algorithm, but then has to be able to communicate that both efficiently and effectively to the people who are writing up the software to implement the algorithm. If you don't explain it well, then they write something up that doesn't work. You waste a lot of time spinning your wheels before you realize that they didn't understand what you were trying to tell them to do. So that kind of communication is very important. You'll probably be presenting some of your work at various conferences. So again, oral communication. And just explaining what you know to clients, to colleagues, even to friends and family. This is what I do. it's good to be able to do that well. Sometimes it's explaining what you don't know. And the last soft skill, there's more, but another major one is management. So teamwork within a group. How do you get along? Are you perceived as somebody who's contributing, who's eager to help? Those are important. And then again, as you work your way along your career, being able to lead effectively, to get others to put the best work possible in for your group. And you'll notice that the technical skills is comprised of a smaller set than the soft skills. You can be really good technically, but if your soft skills are poor, you'll have trouble finding a job, you'll have trouble keeping a job, and you'll have trouble being effective at that job. So I can't emphasize enough working on your soft skills just as you work on your technical skills. So you should be volunteering to give talks at your school or at local conferences, wherever you can go. You should be, because it's like anything else, practice improves your skill set. So you want to get in as much practice as possible. And classes which assign you to work in teams are also extremely useful. How else can you prepare, give yourself an edge? Internships. So there are paid internships where you work at a company and you actually receive money. Those are more competitive, obviously. But even an unpaid internship, if you can afford to do it, adds to your skill set, both from a technical and improving your soft skills point of view. Summer employment. I say summer employment here because most universities in the United States work on a semester system where you take classes in the fall and in the spring, and then you're off in the summer unless you need to take classes to catch up or advance. And so quite often people work in the summer to help make money to pay for schooling. If you can do that in a way that also exposes you to potential careers or different fields and so forth, that's really useful. And student research opportunities. So there are a lot of programs in the US related to doing research during the summer. I'm sure there are similar programs in India. I have several links to internships in the United States, and I was curious if I could find anything in India, and I actually did. So this may be a little small for you to see, but there's a network of national laboratories, and the laboratories some of the laboratories have internships. There are actually far more national laboratories under the Ministry of Science and Technology in India than there are in the United States. So that might be one thing for you to look at. And then relevant professional societies. You guys already know how useful it is to belong to the student chapter of the Society for Industrial and Applied Mathematics. A couple of other societies that I do a lot of work for: the Mathematical Association of America. So that's mathematics. There's another professional society called the American Mathematical Society. The reason that I advocate the Mathematical Association of America is the AMS is more research focused and at the university level. MAA is more four-year college focused and takes into account that a successful four-year degree often leads to jobs in industry and so forth. So there are some resources that are provided through the MAA website and so forth. And then another one that you may not be familiar with, which I mentioned before, is the Institute for Operations Research in the Management Sciences. So operations research was a field that didn't exist until roughly World War I, World War II. So it started in the military arena, and it's basically the science of making better decisions. So using mathematics and scientific disciplines to make the right decision. And so that's a form of applied mathematics, and it is, for example, all the stuff I mentioned before about data science and so forth falls under the Informs umbrella. And there are lots of resources there related to careers in industry. So that's why I mentioned that one. And then the other thing I would encourage you to do is to build your own network. So if you manage to get an internship or to work at a company that's related to your field of study, start building a network. And you can also do this through the professional society membership. The more people you know, the easier it is to help you solve problems that you run into. And by problems, I don't mean technical problems, more like soft skills. So I had a problem here, or I'm struggling with my interview skills or whatever. If you know people, will oftentimes be helpful when you reach out. And the biggest thing, of course, is it is far easier to find a job through networking than it is to just blindly submit your resume to a gazillion different companies. And you can use social networks social media to grow your networks, and things like LinkedIn, which is specifically for careers in industry and business, can be useful. And then, of course, do your own research. So there's more than what I can tell you in 30 minutes about preparing and about finding a job. Here's a link that is actually a meta link. So you go here to careers outside of academia, and then you scroll down, and of course it talks about soft skills, oral communication, written communication, because everybody knows how important that stuff is. But networking, how important that is, so forth. But then down here under resources, there are a number of good links for learning more about opportunities to grow your skill set and so forth, and things related to job opportunities. So from the MAA, the Math Careers portion of their website, from SIAM, the Careers Resources portion of their website. Here's the SIAM video, how to prepare for a job interview. That's got to be good. The Big Math Network, that's also somewhat of another meta layer. If you go into that website, you'll find some interesting things and so forth. And these math jobs and USA jobs, probably less relevant for you guys, although you never know. If you were to apply to graduate school in the United States and come here, then those resources could be useful. All right, so last topic, interview skills, you know, my goal here is if you decide you really are interested in working in industry, then you want to try and find a job where you're going to be successful and be happy. I mean, there's nothing worse than going to a job every day that you don't enjoy. So finding that fit, and it's much easier to be successful if you really enjoy what you're doing than if you dread it. So how do you get that job? Well, when you go for an interview, you should dress professionally, dress up more than you would just going to a class at school. Jeans and sneakers indicate this is just a casual thing for you. So you don't have to wear a suit and tie, but can't hurt. Dressing up sort of shows the respect you have for the interviewer, and that makes them happy, and therefore more likely to hire you if there are multiple candidates who are strong candidates. If you are doing a Zoom interview, or a Google Meets interview, online interview basically, you should still dress nice, but of course you only have to dress nice from here up. I'm actually wearing jeans and sneakers right now, but you can't see that, so it's okay. And make sure that you set up your interview space so that it's quiet and well lit, those kinds of things. When you get into the interview, start off with small talk to break the ice and to get yourself more comfortable. The more comfortable you are, the better you're going to convey your interest and skill sets and so forth and so on. Recognize that it's okay to be nervous. Everybody's nervous, and this is something that's really important, especially if it's a job that you really want. But if you recognize that being nervous is okay, that'll actually make you a little less nervous. And starting off with small talk breaks the ice and gets you flowing so that you're not worrying about how you're doing so much. Be yourself and be truthful. It's much easier to do that than to present a false image. And besides, you and the interviewer are both looking for a good fit. They want somebody who's going to be successful, and you want to be happy working there. So don't misrepresent who you are or what you want, because that could lead to a bad fit, and then you wind up looking for another job. Be ready with questions about this particular company. So do your research ahead of time, get online, read about what the company does, and perhaps what the history of the company is and what their philosophy is, and prepare some questions. That shows the interview you have a real interest in working with them and are not just applying for a ton of jobs and don't care where you wind up. It also shows that you care about the specific job, and that's sort of showing your non-math intelligence. Make sure you understand the interview's questions and she understands your answers. So sometimes they'll ask something and you'll sort of you'll be in doubt and you'll sort of respond. It's better to say, so are you asking, and clarify, so that then you get able to give a good answer. Be ready to bring up your strengths, any evidence of leadership you have, such as being a club president or having organized a seminar, those kinds of things. And a little trick that really is helpful and will make you more confident is have little mini speeches ready to go. So little stories about your background and so forth, and have a few of them so that when the question, this is sort of a trick that politicians often do, they'll get asked a question, they're not sure exactly what the answer is, and they'll just sort of slide into a topic that they do know well and respond with that. So that's a little trick that can be useful to making your appearance stronger. And finally, when you're done, make sure you let them know that you really do have a serious interest in working for the specific company. So tell them, thank you so much for allowing me to interview. I just want you to know that I think I could really contribute, that kind of thing. Say it in your own words, but always finish strong with that. Here's some things to keep in mind, sort of from the interviewer's point of view. The company wants an employee that is capable of doing the job. So that's your technical skills. They want an employee that's a good fit. So that's your soft skills. Mathematicians in general are viewed as problem solvers. So, you know, show that when you're talking that you're a good problem solver. You like that you're interested in working on new things and you love a challenge and things like that. Another really important thing about the mathematicians is that they are able to learn new areas quickly and with little assistance. That's a real strength over job candidates in general. So exhibit this by giving examples for perhaps from the classes that we mentioned before that you might have taken, economics, chemistry, physics, biology. So, you know, I took this class in economics and I worked with this team on solving such and such a problem, and I really enjoyed getting to apply my math skills to this new area. You want to convey that to the interviewer. Any other examples you have, extracurricular examples? So talk about any internships you've had, any work related to the field, clubs you belong to, and it doesn't have to be the SIAM student chapter. It can be the chess club. So, you know, you led the chess club and organized travel for competition and things like that. Also, don't forget that while they have your transcript of what you've taken in school, you want to mention any self-taught areas. So if you have studied Python or R, or if you wrote some software to, you know, perhaps to help organize a club or something like that, mention that as well, because that shows that shows the breadth of your knowledge as opposed to just the depth of your knowledge, and that's a good thing. Okay, so I ran quite a bit longer than I wanted to, but let's go ahead and go into the question and answer session, and I'll stop sharing my screen.
Yes, I'm sure there will be a lot of questions based on this domain, and I'll read them to you one by one, sir.
Manan, may I ask one question?
Yes, sir. Yes, sir. Sure, sir.
Okay. Thank you, Dr. Butler, for your nice and such an informative talk. I have one question. Suppose generally mathematicians are good at developing some algorithm and the mathematical work on paper, and they don't have programming skills professionally. So I just want to know that in this case, someone can apply for the industry position or not?
Yes. So my company, for example, often hires PhD mathematicians who have studied pure math all their life, but really don't have many of the skills that I discussed. But if my sense, I used to interview most of our new hires, and if my sense is that they have the ability to learn, I'll go ahead and hire that person and then have them start working on their software skills. It's not important that you develop the ability to code entirely on your own and so forth. It's more important that you have the ability to understand what software looks like and be able to read it, and therefore you're able to work with an expert in software development in implementing your algorithm, say. So so the idea is you may not know how to construct difficult, complex scientific software, but someone in the company does. You work with them, they implement the algorithm, and more than likely, first time around, it's not working correctly. And so you work with this person, they show you the code they've written, you say, okay, so explain to me what you're doing here. And they say, oh, well, this is the part where I'm trying to implement the data extraction process or something. And you say, okay, so what does this do? And they say, oh, this is supposed to do this. You say, oh, no, that's not what I meant. We try changing this and see if that makes it better. So you're not an expert at all in the computer science part, but you have enough knowledge to work with them. And the same thing is true in other areas as well. So you might be working, we quite often work in new industries. So for example, we might be working for a hospital that's trying to improve their efficiency in their operating room scheduling. So we don't know the details, but you work with a subject matter expert and they explain things and you come up with what you think is a reasonable algorithm, and they look at it and say, oh, no, you're supposed to be doing this, whatever. So it's an iterative process. I'll never forget, I was working on a project for Boeing, and in the project, we were processing this data. The data was basically what they call passive data. So we were getting directions of detection of the sort. And in analyzing the data, we said it seemed like there was a bias. And all of a sudden their eyes lit up and they said, oh yeah, did we not tell you about the such and such bias? I'm like, no, you didn't mention that. Oh, I thought everybody knew about that. No, we didn't know about that. We're not experts in this area. You're the expert. You need to tell us these things. So same thing there. But yes, even if you do not have currently have the background, you're still eminently employable because mathematicians make great employees. I would encourage you, though, if you have the time, to do an online class in something like Python. And so you at least learn the beginning skill set of, okay, this is what a loop is, and this is how you bifurcate in the coding process and stuff like that.
Okay, thank you, sir. Thank you.
So the next question we have is from Ankush. The question is, like you mentioned, how data science as area of applied mathematics really blew up recently. Which other area of applied mathematics do you think could end up as the next big thing?
Manan, can you turn up your volume a little bit? I'm having trouble hearing you.
Yes, sir. Am I audible now?
Yes, much better.
Yes, sir. So the next question is from Ankush, and the question is like you mentioned how data science as area of applied mathematics really blew up recently. Which other areas of applied mathematics do you think could end up as the next big thing?
Well, you know, I don't have a clear answer to that. But what I would say is that data science and all of the related fields and so forth are still very young. So we're seeing different aspects come into play and grow. For example, I'll give you one simple example. So artificial neural networks have actually been around for quite some time, but they've only really recently become extremely useful. And deep neural networks, where you have multiple layers, and the advanced techniques we have now for training those networks enable us to take data sets and train the algorithm to do really useful classification and so forth. But sometimes it's not enough to have what we refer to as a black box algorithm solve the problem, because you'd also like to have some insight of why the solution is what it is. And that's much harder to extract from the algorithm than just the fact that it does solve the problem. Another aspect of these newer type algorithms are a little bit of ethics. So what we've seen is, for example, there are biases in the human classification method. So, for example, in the case of prisoners who are up for parole, and the humans look at certain things and they grant parole or don't grant parole, and then you say, oh, well, we could use a computer program to take the bias out of that and make it purely objective instead of subjective. But if you're not careful, especially if you're using machine learning type techniques, the machine will learn the biases because you're using training data, which has biases incorporated in them. And so the machine actually ends up learning the bias. So you say, well, I developed a machine learning algorithm that does this classification, so therefore it's not biased, and that's simply wrong. So learning how to show that your algorithm is not biased, or how to develop one that's not biased, is another aspect. So I think I don't have an answer to what's next after data science, but I will say that there's lots of new areas within the broader field of data science where things are popping up and growing.
So the next question is about your experience being a vice president at the Daniel H. Wagner Associates.
Well, so I was actually president and CEO until last year, and then I'm retiring, and so now we have a new president, so they had to give me a title, and they were going to give me a title of president emeritus, but I'm not old enough to be an emeritus yet, so I decided that I would just take on the title of vice president. So in my company, and it's a little bit different, it's a company of mathematicians. So most companies at the more senior level, the management level, the executive level, the executives are not mathematicians. They're people with expertise in whatever field the company is working in. And then they hire mathematicians or have a group of mathematicians who work on them. Our company is entirely mathematicians, which means that we have to wear many hats. And I actually did not necessarily want to become president, but I felt like it was that I could do the best job, and it was an extremely important job to keep the company doing well from a financial perspective. And so I took on this role, I think 2006 or 8, something like that. I forget. Anyway, it's no fun. Being a mathematician and working on cool problems and the software solution, seeing that the algorithm we came up with really does work, and seeing people use the algorithm for other applications and so forth, that's fun. And even writing proposals where somebody has a problem and you think, gee, I wonder if we applied such and such a technique that would be successful. And so, you know, you do the research to be able to write a successful proposal. You're learning new things. I mean, I've learned a ton of different mathematics in different fields throughout my career. Being president, I still got to do a certain amount of that, but I also spend tons of time worrying about the finances of the company, worrying about personnel issues, the human resources side of things. Are we following the right rules and regulations? Dealing with the government on the Department of Defense type contracts. Those contracts are a real pain. They will oftentimes call out regulations saying you're not following them, when we're not following them because it does a better job for the government. But government doesn't care. No, I shouldn't say that. The government, oftentimes, the bureaucratic part of the government is all focused on following these rules, even to the detriment of the government or the contract itself. And if there's a problem between the people working on the contract and the government, the president has to get involved. So, on the other hand, I have much more autonomy and get to choose to do some different things because I'm the boss. So that part of it was nice.
Thank you, sir. The next question is like, as an undergraduate, he wishes to know some reasonable and manageable skills that he could equip himself with for research and industry internships in data science. And what would you expect from an intern for your company?
Well, to be honest, again, the soft skills are more important than the technical skills. So, and we know when an intern comes in that they don't have the technical skills to work on the really challenging problems, but they may have good enough skills to do some basic data analysis, for example, or to be doing some of the testing and then looking at the results and saying, yes, this is what we expected, so it's good. This is what we expected, it's good. Oh, there's a problem here. This is not what we expected. I don't know how to solve the problem, but the point is I saved somebody at the company from having to go through all that stuff, look at it themselves and cut it down to this one's a problem. Now the people who understand it can work on it. So when I'm looking to hire an intern, I'm more focused on, are they really interested in coming to work here? Are they excited about the opportunity? Can they understand easily or explain easily different things. Is it somebody I'm going to enjoy mentoring, or is it somebody who's going to be a pain? That kind of thing. So I can't emphasize enough how working on your soft skills is going to increase your success, not only in finding a job, but in finding an internship.
If there are any more questions from the faculty or from the students, so you can enter them in the chat box.
Well, actually, I have kind of a tight deadline here, so it's 10 o'clock now, and again, I want to thank you guys for. I'm very impressed by the number of people who came to the talk, the number of students and perhaps some faculty, and I enjoyed it. I enjoyed the questions, and I wish you all the luck in the world in the rest of your academic career and your career beyond graduation.
So with your permission, I would request everyone to please switch on their camera so we can take a screenshot of this seminar, as it will be a memory for us. So yeah, thank you all. The photo is taken. And now I would like to conclude this session. And for that, I like to start by expressing our gratitude towards Dr. Butler. Thank you, sir, for making us familiar with the business, industry, and government, abbreviated as big careers for mathematicians. I'm sure that all of us found this session very enlightening, and it will surely help us in our future projects. I would also like to thank our Honorable Vice-Chancellor Professor Rajendra Kumar Sharma and Faculty Advisor Professor Dr. Vivek Sehgal for attending this seminar and for supporting and encouraging us to take such initiatives. Also, we owe special thanks to our founding president Achyut Tiwari sir for organizing this seminar and the members of the executive committee for joining this session. Thank you all for being a
Thank you.
Thank you, Dr.
Bye, everyone.
Bye. Thank you.
Bye.
Thank you, Manan. Nicely conducted.
Thank you so much, sir. Thank you so much. Thank you, sir.
Thank you, man. It's
Thank you,
perfect.
sir. Thank you.
Okay.
Thank you all the faculty for joining me.